for coming. I'm wearing this shirt to remind you to go to the March for Science, please, on Saturday. Anyway, I have a lot of material to cover, so let's get on to it. Let's see. First of all, I want to acknowledge I'm up here, but a lot of people have done a lot of this work. I'm often going to say we, this is the royal we. A lot of people sorted the samples, went through the stinky stuff, and did all the work that now I'm presenting. This is a list of those people. So thank you very much, everybody who contributed to this research. So this is my roadmap. This is what I'm going to cover. I'm going to start with a few slides to tell you why we're doing this work, some motivational slides. Then I'll give you some background. I'm not assuming everybody here knows a lot about seabird foraging, so I'm going to give you a few slides describing some of the really cool patterns that relate to tropical seabird foraging ecology and why, in my opinion, those patterns make seabirds very good indicators of conditions in the ocean. Then I'm going to run through 3 case studies. I'm going to tell you about a community look we did in Turn Island, looking at a bunch of species at the same time, and then our efforts to develop both a local indicator for Oahu and a regional indicator for the Northwest Hawaiian Islands in terms of plastic distributions through the stomachs of seabirds, and then a few slides on emerging or new issues and thoughts. Okay, so the motivation is, well, I'm sure everybody here has heard about, you know, the plastic gyres and the garbage patches and all those kinds of things. So everybody's trying to figure out how much material is out there, how much is the amount increasing or decreasing over time in terms of the size and the types of material. So to give you a sense, we're talking about things as big as a VW Beetle car, like, you know, this huge pile of netting, macro debris, all the way to tiny, tiny little less than 1 millimeter pieces. This is the range that you can see with your naked eye. Our work doesn't get into the really small micro beads and all those kinds of things. I'm going to be talking about a few centimeters to a few or almost 1 millimeter, which is the range of material types and sizes that the seabirds I study are ingesting. But basically, this is the big picture, the driver for our research as far as today is concerned. Is plastic going up, going down? Is it changing in the global ocean? Well, maybe you've heard a lot of people are going out on ships and trying to answer this question. The problem is ships move about 10 miles per hour, and the ocean is very, very large. Then when you go on a ship, well, you know, we put out a little net out. It's about 1 meter by 2 meters. We tow it behind the boat, and we collect a bunch of material. We sort it and all that. Very time consuming, very expensive. A ship is about $10,000 to $20,000 a day. So, you know, big ocean, very slow, very expensive. This is helping, but it may not be the complete answer we're looking for. So basically, the solution I propose, and I'm giving kind of this take-home message to you now, is why don't we let the birds do the sampling? They go to the ocean every day. This is part of their job. And as part of their job, they collect prey, and they unfortunately ingest marine debris. So if we could collect the debris and the prey that they are harvesting at sea, we could use them to sample the ocean. Why are seabirds useful samplers of the ocean, and in particular plastics in the ocean? Well, there's 2 big reasons. The first one is they're very abundant. They travel very far, covering large expanses of the ocean. And when they come home to breed, they do so often in huge colonies that are very predictable and persistent over time. So we can go there and we can sample a fairly large amount of individuals. Furthermore, there's many different kinds of seabirds, and the really cool thing is they forage in different ways, in different areas, and they eat different things. So if we pick the right species, we can get a good sense of a big range of types of sizes, types of materials of plastic, different areas of the ocean, the surface versus mid-water layers, those kinds of things. We have a whole palette of flavors to choose from, so we can develop monitoring mechanisms for specific types of plastic areas, sections of the water column. Here's the background. The first thing I want you to realize is basically rephrasing what I just said. Seabird researchers have spent a lot of time. This is a seminal, really awesome paper from 1971 where Ashmole described different ways that seabirds collect food from the ocean. And different diagrams depicting the variety of ways that they're doing this. This is for a tropical ocean, so we don't have things like penguins and things like that. But what do we see? Well, some predators collect material in the air or walking on water, like storm petrels. Others plunge or dive, like terns, tropic birds, and some shearwaters. Others actually collect material just at the surface, paddling around, like albatrosses, shearwaters, and petrels. Again, reiterating the notion that a bunch of different types of foraging mechanisms at our disposal. And as you can imagine, these different foraging mechanisms will collect prey, but also different kinds of plastic. In particular, when we focus in the tropical ocean, there's 4 types of foraging that are very pervasive and very typical here, and we often don't find them in other parts of the global ocean. Pursuit. This red-tailed tropic bird is diving in to catch a flying fish that has been scared off by the bow of a ship. A lot of tropical seabirds do this, using tunas and dolphins to scare off the prey into the air. Surface plunging. This is a poor attempt at a dive by a little shearwater, trying to keep the big wings out of the water. This is sort of the most this species really can go underwater. Pretty sad if you compare it with cormorants or penguins. Plunging. This is, again, another really tropical mechanism for getting underwater, trying to go to 10 meters below the water by overcoming the buoyancy. This is a brown booby from Lanikai. And surface picking, another very typical thing that things like frigate birds often do. So, okay, so they feed in different ways, and they then have a chance to eat different things and so forth. What else do we know about tropical seabirds? Most important lessons that I would like you to get out of this, which makes them very good mechanisms for sampling plastic in the ocean, is that they're very opportunistic, which means basically if it's at the surface and it fits in your mouth, eat it first and ask questions later. Studies, lit reviews, or big dietary studies, they find absolutely amazing things in the stomachs of many of the seabirds that breed around here. Any guesses what this could be? Has anybody seen one of these before in the ocean? Just say it out loud if you know what it is. By the winged sailor, maybe 95% water. It's it's like a little gelatinous zooplankton. Well, albatrosses eat a lot of these. How about this guy? On the beach in Kailua and in Waimanalo at the high tide line. They're as big as a little grain of rice. This is Halobates. This is a water strider. There's a bunch of small petrels and storm petrels that about 80% of them have these guys on their stomachs. Again, tiny, tiny little things. A lot of things like and flying fish and eggs and things like this. So a lot of these are ingested by some of these far-ranging surface foraging albatrosses and petrels, suggesting again that go very far. If you run into something that fits, it looks right, eat it. Again, if you're doing that and you're running into plastic, the chances a lot of these birds are going to ingest the plastic, making therefore them good indicators of what's out there in the ocean. Another really interesting issue, especially for oceanographers like I am, is that many of these birds are using some of the features in the ocean to find the food. This is apparently a very boring picture of temperature in the ocean, showing you, this is this is Madagascar. Here you see Africa. There's warmer water in the north, colder water in the south. Looks terribly boring. However, when you look at the rings, the eddies, the sea surface height, you see that this is a very dynamic landscape with warm and cold eddies. And then all these little dots show places where frigate birds were foraging, and they were foraging on the edges of these features, suggesting that frigate birds patrol the edges of the eddies, where perhaps their food becomes concentrated, places where plastic also becomes concentrated, therefore again making some of these species pretty good indicators of how this material is distributed at sea. And now my final slide is concerning the sort of the take-home lessons or the background of how do tropical seabirds forage. Is a lot of them rely on subsurface predators, marine mammals and tunas, to drive food close to the surface. There's a lot of references that discuss this. About 90 species from 27 different genera are doing this. For many of these species, this is the dominant way that they make a living. This is the main way that you find them locating food and foraging. This is so persistent that actually we have here in Hawaii, you may know this thing, this tuna bird community that has been described in the Pacific and the Indian Ocean and the tropical Atlantic Ocean. These are birds that are really associated with tunas and mammals. So why does this matter? Well, if we can understand the type of material that these birds are ingesting, maybe through their food, and this is the same food that tunas or marine mammals are ingesting, and we like to eat the marine mammals, well, not the marine mammals, sorry, the tunas. Just checking if you're awake. You know, maybe there's interesting connections between the birds and the tunas and maybe people down or up the food web. Another reason why it seems like an interesting thing to focus on these tropical seabirds. Okay, so the objective then, now that we're all seabird foraging experts, the objective now is going to be to devise ways that we can sample plastic in the open ocean, pelagic plastic. And when I say that, I want to refer to two aspects. We want to know how much and what type of material is out there. And the goal is going to be to devise methods to do this with different Hawaiian seabirds. So we want to develop methods to do this, and we want to establish some metrics for monitoring this pollution to get a sense of how bad is it getting better, is it getting worse, and so forth. Okay, so the first case study is Tern Island. You see here, this is what Tern Island looks like. It's basically sort of like a man-made stationary aircraft carrier with a bunch of birds and a little bit of people that go out there to monitor the birds. And this is where Tern Island is located, towards the southeast end of the Papahānaumokuākea National Marine Monument. And what do we have here? Well, this is an amazing place because there's 16 species of breeding Hawaiian seabirds nesting side by side. And furthermore, they represent a bunch of different foraging guilds or strategies based on not only what they eat, but how do they collect this material at sea. So this is a perfect place to do an experiment. We can go out here, we can sample a bunch of the plastics that they're collecting, and we can better understand how some of these species are more exposed to plastics than others. Okay, so this is the characters, the birds we're going to be looking at, and I'm going to show you what guilds they represent. Well, we have albatrosses. We have suliformes, a bunch of boobies and frigate birds and some tropic birds. Then we have what are called the tuna birds. Remember those guys? They love tuna and marine mammal foraging associations. Yet a taxonomically very diverse group. We have some terns and some naughties, and we have some shearwaters in there. Then we have what are called nocturnal petrels, 3 species of little petrels and storm petrels that forage at night. And then we have the nooston feeding terns. These tiny little terns that eat very small prey at the surface, noostonic prey. Okay, great. So you've seen that list of species. Who do you think is the species that's the most dirty? The one that has the highest incidence of plastic? And by that I mean, if I took 100 of these birds and I looked in their stomachs, which one would have the highest number of birds with any plastic? Albatrosses, right? We all think the same. You know, we've seen the photographs and the dead chicks full of sliders and all these things. Okay, any other takers? Any other ideas beyond albatrosses? Shearwaters, maybe? Well, I'm very happy nobody has said. Wow, Who are these little guys? Well, they're really small. They live underground. They're sort of under the radar screen. When you look at them, we looked at a total of 58. And you notice here what I'm showing you for all of these species is going to be the incidence, again, the percent of birds that had any material, any plastic. Then I'm going to show you, to be fair, so you can I can show you whether we have a lot of evidence or not. I'm going to show you the number of individuals that we analyzed. So in this case, 57 chicks were analyzed. All of them had some plastic. Chicks are much easier to sample because they die more frequently in colonies. Adults don't really die very often. So we only had one, but it had plastic. So 1 out of 100%. Okay, this is the dirtiest bird we got. Okay, do you want to consider your answer? Do you want to still stay with albatrosses, or you have any other options? Everybody's thinking, what looks like a Tristram's from Petrel? I don't know, another little... Remember those nocturnal foraging petrels, maybe? Those guys could be super exposed to plastics? Well, yes, the bunny petrel. This guy, a lot fewer of these birds available for us to sample. We only had 5 and 1, 100%. And you may say, well, it's a very small sample size. You're right, it is terribly small, because we're not killing any birds. We're only using the ones that naturally die. And this is a massive constraint. But still, if we do this long enough, we can build up sample sizes. And now, actually, I have about 100 bone petrels in the freezer. And Lauren, who's sitting over there, started chopping them up. And I think she's pretty much getting the same rates. So this is looking promising. Okay, any other takers? Let's see. What other species do you think have high plastics? Well, somebody said albatrosses. Maybe. Are we at albatrosses yet? Finally, albatrosses. You notice they're not at 100%. Chicks, a fairly big number, because we were doing a demographic study on them, looking at their growth rates and so forth. They had a fairly high rate, 96.7. Adults, 89.5, with 19 adults that we were really lucky to have. There's blackfoots. You may be surprised how low blackfoot adults are, only about 58%. And then wedge-tailed shearwaters, very few of those, but also pretty high rates. So these are the birds that had over 50% in any of their age classes. They have one thing in common. It has to do with their taxonomy. Any taxonomy buffs out there? What do all these birds have in common? They're tube noses. They're, procellariformes. And I'm going to show you in a second the reason why we think there's a very key shared feature of all these birds that makes them really good at retaining the plastic that they ingest. Okay, let's move on. Now I'm going to show you a graph here that shows you now for common species and age groups where we had at least 8 or more birds that we sampled. What I'm showing you is, just like I did before, the incidence from 0, nobody had plastic. Sooty tern adults had no plastic. That's pretty nice. To the birds that had 100% plastic. Over here, TRSP, Tristram's from Petrel chicks. Okay, so you notice, well, not everybody has plastic. Some have a lot of plastic, others don't have any plastic, and there's sort of a ramping up of different species. So we have, a continuum perhaps. Let's then just for fun put this is the 50% and the 25% line, just to sort of, give us a ruler to see the ones that are really sort of in bad shape, the ones that are halfway there, and the ones that seem to be doing better. And that's the Tristram storm petrel chicks. I want to spend a little time on them because they're so fascinating and we know so little about them. So then you see here the Laysands, the chicks and the adults, and the Blackfoots, chicks and adults, right? And those are the 5 species that had any age class over 50%. Okay, so some of the things when we do statistics, we see that Laysan albatrosses have higher incidence than Blackfoots, largely because of the big difference between the adults. The chicks are fairly similar, and chicks have higher incidence than adults across both species. Chicks are being provisioned a lot of food, and they're really packed, and then they barf it out as boluses. I brought a few boluses over there. Later we can look at them if you like. Okay, Well, not only that, right? Incidence is only one thing, one aspect of exposure to this plastics and so forth. Another really good way to think about this is how much do you have? What's the load or the magnitude of the amount that you carry? I have this picture here to highlight two things. The first thing I want you to notice is that we have beefle, blackfoots, laysan, and tristram petrels. This is a log scale. So these are really little numbers, and these are fairly big numbers. These are grams. So the biggest numbers here are close to 100 grams, which I guess 100 grams, it's, I'm not very good with non-metric.
About
3 ounces. Okay, about 3 ounces. Thank you. Okay, so first thing to notice, remember we said the chicks have higher incidence than the adults. Well, not only that, they carry a lot more plastic. This is chicks and adults, chicks and adults. Substantially more plastic than the adults. So that's the first thing I want you to remember. The second thing is, look at this little Tristram petrels. They have amounts of plastic that are comparable to laysan and black-footed albatross adults, but they are very, very small. So perhaps to make this more fair, I could show you the percent of body mass that the plastic accounts for in these birds. For blackfoots, it's always less than 4%. For laysans, it's all the way to 12%. There was some of these chicks over here, they were close to this 12% threshold because they were not fully grown. And Tristrams is about 2%. Okay, so maybe we can rescale it that way and consider, you know, how much do they actually have. And again, this idea that chicks have a lot more than adults because they're being fed and later they discharge this material before they leave. So perhaps if we want to monitor seabirds, maybe it would be really good to look at the chicks. They're hostage, basically. They're at our disposal. We can weigh them, do all these things to them. And on top of that, they seem to really be collecting all of this material. Some of my students actually looked at the curves showing how the material accumulates as the chicks get older. Okay, so the Tristram petrel, remember, right? The tiny little guy, 100% incidence. This is what a little Tristram petrel chick looks like. Up close, you see the tube nose, very characteristic. And this is what the material they ingest looks like. This is 10 millimeters or 1 centimeter, the side of these squares. So these are really tiny little pieces. They're also very colorful, really amazingly colorful. And they're mostly fragments, hard pieces of plastic. Well, remember I mentioned why tube noses or prothellariformes. This is a picture of what their gastrointestinal cavity looks like. The really cool thing is they have two very distinct chambers. This is the esophagus, the food comes here. This is what's called the proventriculus, or the forward part, the forward chamber. It's expandable, thin-walled, is like a balloon. Very good for storing large amounts of food that would be delivered, and oil and squid chunks and so forth. And very good with chemical digestion. After that, we have the gizzard. This is basically like the teeth of the bird. Very robust and muscular, very good for physical digestion, especially some of the birds will ingest little rocks to grind up the squid beaks and the fish bones and eventually the plastic. And then we have the intestines down there, but we don't really look at the intestines. We have a little bit, but it's pretty nasty stuff. So we stay just with the proventriculus and the gizzard. And the food travels this way, and it really seems like there's something special about these petrels, because regardless of their foraging depths or foraging gills and so forth, you see even the tuna birds that are petrels have high rates of plastic, and the albatrosses have high rates, and the storm petrels have high rates. And maybe this is the key. So whenever we do our work, we really focus on comparing what we see in the proventriculus with what we see in the gizzard, and we treat those two chambers differently because they behave very differently indeed. Okay, so this is sort of what the Tristram petrel would look like. This is a sample. You know, you see a bunch of this gray, mushy, it's sort of like a squid milkshake with a little fishy aftertaste. You can see little plastic pieces. There's little pieces of halobades in there and so forth. Then this material gets sieved through a 0.5 millimeter sieve. So that's why, remember I said, really we're losing things that are about less than 1 millimeter or so. Then it gets separated out into food and non-food items. And basically, out of all these samples that we get, we separate them into 3 parts: plastic, natural food, usually hard parts, squid beaks, fish bones, eye lenses of fish and squid, and then natural non-food, which is things like pumice, twigs, seeds, things like that. So what do we see for the Tristram's from Petrel? Well, what we see, first of all, again, this is a sample from one bird. We see that they have a lot of material. All the birds we looked, those 57 birds, had a minimum of 32 pieces to 615 pieces. Huge amounts. They're tiny pieces, but still, you know, the numbers look really astonishing. Furthermore, if we separate them into the Proventriculus and the Gizzard, we see these distributions of the sizes in millimeters. So most pieces are about 2 to 4 millimeters in length, but actually these are the ranges, and the Proventriculus has significantly larger items than the Gizzard, suggesting that, you know, there's this mechanical degradation, or maybe the little pieces make it into the Gizzard, the bigger pieces do not make it into the Gizzard until they break up. So significant larger fragments in the Proventriculus, and also a lot more plastic mass in the Proventriculus than in the Gizzard. This is comparing, every circle compares the same bird, its Gizzard and its Proventriculus. And you see we have a lot of outliers out here where the bird had, say, 2 grams of material in the Proventriculus and only 0.1 gram of plastic in the Gizzard. So really suggesting, again, that, you know, this material is coming into the Proventriculus, getting ground up, and then becoming smaller and moving on. Okay, and then I was going to show you a picture of some of the food items that we found. This was pretty time-consuming work, and it was really, really hard to count things because we were finding things like little legs of water striders. So basically, we had to resort to just detecting, are they there or not, like we do with the plastic. So what do we find? Well, we find, a lot of water striders, a lot of squid beaks, pelagic snails, fish bones. So these are food remains. And then we find non-food items like a lot of pumice and a lot of seeds also, pretty interesting. A lot of tiny little portulaca seeds, things like that, which, you know, we don't know if the chicks are collecting them on the colony or the parents are collecting them because they float. That's sort of a bit of a mystery. But basically this suggests that, you know, they're eating things like that, very small neustonic organisms at the sea surface that are collecting along with this plastic, and then some vertically migrating prey, like some of these metophytes and flying fish that are at night coming up and becoming available to the birds close to the surface. So that first idea, that first case study showed you how not all birds ingest plastic equally. Petrel seem to be the ones that are taking most of the material. And I wanted to highlight this little beautiful jewel of a bird, the Tristram's from Petrel, that is sort of falling through the cracks because we're also focused on albatrosses. But these little guys have large amounts of plastic. And, you know, they make a living in a way that seems really conducive to picking it up because you're eating little tiny blue and black and yellow and orange and red prey items at the surface that looks just like the plastic they ingest. Now let's move on to looking at how to sample the ocean using seabirds. So I'm going to take you now all the way to the other end to Curie, looking at some regional metrics. And what we're going to do now is focus on our good old friends, the albatrosses, right? Remember, the chicks have a lot more material than the adults. They pack it up and they throw up this bolus, this like a giant owl pellet full of squid beaks, pumice, and plastic. So the goal is to collect the material, to sort it. You find a lot of identifiable fancy things like a nice comb. And then we separate everything into all the different sizes and types of material. We measure it. Basically, we're trying to understand what component of the plastic is this black-footed albatross sampling in the ocean. So we always consider 4 categories that have to do with the way these items could harm a bird that eats them. The first one is fragments. These are hard, not very flexible. They can have sharp edges. You know, you wouldn't want to eat something like this, perhaps. You know, they could be anything. You see a bicycle reflector up there and a lot of pieces of things that we really can't tell what they are. Bottle caps, for instance, are fragments. Pellets or noodles are fragments. Foam. Foam can be anything from styrofoam to, you know, the insulation you use for windows and anything in between. Line. A lot of, not just monofilament, but a lot of burlap bags that break up, or the big lines that are used for big cargo ships that then come undone and are eaten by the birds as flying fish lay eggs on. And sheep. So these are the 4 categories that I'm going to be referring to consistently. The Tristan storm petrel was eating 97.5% fragments. Albatrosses are much more sort of diverse. They eat bigger things and they eat a lot more types of plastic. And again, these are the fragments. We're very fascinated by the color and the sizes of these fragments. Okay, so every bolus contains plastic. That's the first thing that I would like you to get. So incidence is 100%. So that means that we cannot really use incidence anymore to keep track of plastic pollution through albatross stomachs because every bird has it. So we have to get more creative and maybe use, say, mass or volume of the different components. Overall, on average, 70% of a bolus from Cure for a Blackfoot albatross is plastic. Okay, so here you see plastic. Again, these are the median, the 75, 25, 95, and 5 percentile. So this is the distribution. Most of the material in the bolus is plastic. And then there's some food remains and non-food items. Okay, if we focus on the plastic, what do we see? Well, we actually see that black-footed albatrosses, they really have a tendency to ingest mostly line and foam. These are the dominant types. Fragments, a distant third, and sheets, there's just traces of them. They're not very durable, they're really light, so okay, that's what we would expect. But this emphasis on the line is very interesting for the black-footed albatrosses, and it's very different from what Laysan albatrosses do. Looking at the fragments, we see these are the size distributions, and you see a much wider range of sizes from 1 millimeter all the way to 73 millimeters, 7.3 centimeters. And here we have boluses, and then we're comparing it with stomachs because we had some stomachs just to see if there were any differences. We don't really see a difference, but we see a huge range of sizes, even though you see there is this peak sort of at the lower end, less than about 1 centimeter in length. Okay, well, this is all great. You know, we can do this in so many ways. You know, I could spend years turning the data backwards and forwards and doing all these things. And you may say, so what's the point? You know, why are you doing all of this? Well, this is just one part of it. The second part of this study is trying to understand where is the material coming from, right? We want to know what it is, how big it is, so maybe the models of ocean circulation can give us information about how this material moved through the ocean. But an integral part of this is also understanding where do the birds go to get this material. So at the same time that we were doing this study with the plastics from the chicks, we were tracking some adult birds. So this is Cure. These spaghetti loops show 14 trips where the parent went to sea and came back. And then you see all these brown circles are seamounts. This is the emperor seamount chain. And then the colors depict deeper or shallower parts of the ocean. So the first thing that you see is all of these birds went to the western North Pacific. None of these birds came over to the central or the eastern Pacific. Just for reference, birds from Turn Island all come here to California and come back. These birds are going west. And furthermore, they are spending a lot of time, given how small those features are, around seamounts. This is now showing you their amount of time spent at sea. It's kind of hard to see, but I want you to look for those little red specks, which are high-use areas. They spent, on average, about 10%, almost 11% of their time close to seamounts. The rest of the time in deep ocean waters. So we know they're collecting it from the west. Also, we know they seem to spend a bunch of time around seamounts, places where a lot of trawling for tuna is happening. Perhaps places where this material is becoming concentrated. We need to look more into it, but it definitely suggests this marine debris is coming from that section of the ocean. So some of the implications: Curie blackfoots collect plastic from the Western North Pacific. Plastic incidence in boluses, not a sensitive metric. Every bolus has plastic, so we have to look more at the amounts, not just presence, absence. And therefore, we're also starting to try to focus more on the types and the loads of plastic, and also trying to get at the size and the color to try to understand how they're collecting it, and perhaps even the origin. And the really wonderful thing about albatrosses is because they're collecting bigger items, some of the items are recognizable. A lot of user items, bottle caps, little soldier, an oily glove, maybe from a long line boat, who knows. But we can start trying to do some detective work and trying to understand where is this material coming from. And again, that is the goal, to try to figure out ways to perhaps stop that flow of that material into the ocean. Okay, getting to my third case study. This is the local metric, looking at the Wichita shearwaters here on the islands. And again, they're really interesting because they forage with skipjack tuna. They love skipjack tuna. They hang out together, and they must be eating the same things because, you know, they isotopically, they're very similar also, and they hang out together. So this is brand new data from our colleagues at USGS. These are birds from Marine Corps Base, Hawaii, that were tracked. They had chicks on the colony. All these little colorful spaghetti loops are their movements. And basically, the take-home message I want to give you is they remain within 200 miles of the islands. So during the breeding season, these birds tell us the plastic that is within 200 miles of our island. This is a local indicator. Very different from the albatross, a very pinpoint look. And again, because there's also different colonies, perhaps this could even be done throughout the Central and South Pacific to try to get a sense of how different islands compare in terms of the plastic that's in the marine environment around them. Here we get the birds that fledge. Some of the islands, the offshore islets around here. This is a picture of a little wedgie thinking about it. You know, all fluffy still, thinking, oh, is it time to go? Maybe I'm going to get ready to go. A lot of them, unfortunately, don't make it. They end up at Sea Life Park, or they end up being hit by cars on the road and so forth. We get them, we necropsy them, and basically this is what it looks like. This is the stomach open, and you see all these colorful little fragments of plastic that we find inside of them. We looked at all those things, the size, the number, the colors, all these kinds of things. And because these are really little birds, they're eating very small fragments. You can see here the range, again, less than 1 millimeter to almost 8 millimeters. This is a classic sort of piece that comes from a Wichita shearwater. A lot of white pieces, flat, rigid fragments of that general size. On top of that, we get a lot of squid beaks and eyes of squid, lenses and things like that. This is one part of the beak of a squid, the other part, and these are 4 eye lenses. So we get a lot of this material. And again, because we're trying to understand not only the plastic they eat, but how do they fit into the ecosystem, we're quantifying all the squid beaks and so forth as we go. Okay, so we've done this for 2 years. We've done a few more, but this is sort of the 2 big years when we did a big effort to really get a handle on how many samples we needed. And here you see the gizzard and the proventriculus, right? The bag and the muscular second chamber. We have the 2 years, the number of birds, the percent that had plastic, and the percent that had beaks. And you see the percents with plastic, you know, they seem to vary from year to year, and the gizzard seems to have much higher than the proventriculus. On the other hand, the gizzard also seems to have a lot more squid beaks than the proventriculus, maybe suggesting is a place where material gets stuck, gets retained. Okay, so let me ask you, we can do a few statistical tests and try to answer some questions about this. Would you say the probability of finding plastic is influenced by whether you look in the stomach, the proventriculus, or the gizzard? Well, yeah, in both years, the gizzard looked higher than the proventriculus. So yes, there was more plastic in the gizzard than the proventriculus. Okay, how about the year you look at this? It would be interesting to know whether, you know, can we just sample 1 year, or do we need to do this over many years and sort of get a sense of how things change with the oceanography or with the prey that comes in and out and so forth. 2009 and 2010, it looks a little higher in 2010, whether I look at the proventriculus or the gizzard, and yeah, there you see it. So again, we're trying to build a sense of how these things vary and what are the factors that influence those amounts of plastic that we see in this species. In this particular case, there's definitely an organ issue. So if I'm only going to look at throwing up birds, I'm never going to sample the gizzard. I'm not going to get the whole picture. And there's also a year-to-year difference. Okay, so this is what we did in 2009 and 10, but then we've done a few more of these, and I just want to show you sort of since then, what have we found out? I put up here this result from Fry, maybe you know him. He did a study in 1984 where they collected 20 adults, and they had 60% incidence. 12 out of 20 had plastic in 1984. This was right off, I think it was from Manana that he collected them, breeding adults. Well, we were able, because of a bad situation, we sampled 28 adults that were killed in Marine Corps Base Hawaii by dogs. We looked at them, same methods, everything the same. We had 71.4% incidence, and it's actually higher. It's significantly higher than what we had in 1984. And then we have some data from the young birds. Here I show you, this is the summary for the data I showed you before, where we had overall 72.5% of incidence. And then we had other after hatch year birds, so not first year, but not for sure breeding age yet, 62.2%. Suggesting again that maybe the chicks have again higher rates than the adults. So maybe the chicks is really a place where we can focus our work, not only because of the easier logistics, but also because they seem to be sort of this receptacle that is being provisioned all this plastic. So what are some of the implications? Well, again, breeding Wichita shearwaters collect material 200 miles away from us. This is a local indicator. Some of the next steps, well, this year-to-year variability is very troublesome, because to me it suggests either the ocean moves plastic in or out of this 200-mile box, or the food that has the plastic and leads to ingestion by the birds is coming in or leaving. Something's happening. You know, the plastic in the ocean doesn't change from year to year based on our inputs. There's something else that's leading to this change. So I'm really interested in figuring out what this is. And I'm really thinking this link with prey ingestion, because there's a definite link with squid beaks. The years where there's more squid beaks, there's less plastic. And the year where there's less squid beaks, there's more plastic. Well, what else do they eat? They eat a lot of flying fish. So I want to sample flying fish. It's really hard, but we got to get some more flying fish and look and see, because I would bet, I don't have a farm, but I guess if I had a farm, I would bet at my farm that maybe there's a bunch of plastic inside of those flying fish. And there's sort of this dipole. Warm years, more squid, less plastic, colder years, more flying fish. I don't know. That's kind of what I want to look into. Okay, so finally, we're getting to the end here. I just want to show you some emerging issues. We've been looking at other species that here around Oahu we get from Sea Life Park. We necropsy everything we get. We're building this library of isotopes and tissues and so forth. We found plastic inside of a white-tailed tropic bird. Very, very unusual, never documented before. It looked like this little blue piece, and we thought, wow, that kind of looks like a flying fish. Then later we found a very similar looking blue piece of plastic inside of a mahi-mahi. And I was thinking, you know, it's again about flying fish. There's this, now these plastics look like flying fish, and these predators are ingesting this stuff because they just plunge on it and take it. We've also seen a lot of plastic, 60%, the highest rate we've seen so far on tunas for aku. So we're slowly building up this broader picture of some of the other birds. So finally, just to remind you, petrels, no matter what foraging guild they belong to, they have high rates of plastic ingestion. Surface feeding, dipping, well, this is a frigate bird, which I put in there too, to suggest that, well, maybe other birds that also are collecting material from the surface may be also susceptible to plastic ingestion. This is sort of a bit of an unknown thing. And then branch divers and tuna birds, also new groups that people globally have not really been concerned about, are also showing higher rates of plastic ingestion. Things like brown boobies, brown noddies, red-footed boobies, red-tailed tropic birds, and of course the wedge-tailed shearwater. Good news, sooty terns and brown noddies, we have not seen any plastic inside of those guys. So, yeah, I just want to show you really fast. Thank you very much for coming, and to everybody that funded and helped and did things to help us out. And I can answer any questions you may have, and I can meet you over there, and I can show you some samples. Thank you very much. Okay.
You have about 15 minutes for questions.
I have 15 minutes. Yes.
If the chicks have 100% plastic and they're fed by the parents, how can the parents have less than 100%?
The question is, how is it possible that chicks have 100% but adults have less than 100% when the plastic goes from the ocean to the parent, from the parent to the chick? Well, what happens, right, is the parents are offloading this proventriculus full of oil, squid chunks, fish eggs, and plastic onto the chicks. So remember, when we looked at, well, I didn't show you. When you look at the albatross adults, most of their plastic is in the gizzard. Their stomachs are empty. They don't have any. They have tiny little pieces in their gizzards. So that's why, you know, if these adults haven't ingested plastic for a while before the moment that you get them, they may be empty, even though their proventriculus could be full, but that was offloaded to the chick, right? So they're basically, you know, they're like a shopping bag, right? The stuff goes in and then it goes into the chick, and their proventriculus is empty. So usually adult albatrosses have plastic in the gizzard. Small fragments, not really in the, yeah.
This is kind of related to the, in the chicks' food bowls, do they purge the plastic while they're, or squid beaks or whatever while they're growing?
Yeah, the question is, do the chicks expel the plastics and squid beaks and so forth in a bolus? So not all species do this. Albatrosses do this, storm petrels do not, shearwaters do not. There's one shearwater in Tasmania, the flesh-footed shearwater, where there's been documentation of little like bolus-like piles of squid beaks and plastic that they find in their nests. So, so yes, a lot of the chicks cast these boluses, which provide a nice record. You can go check out the ones over there of what they've been ingesting. The really cool thing is, my student Dan looked at chicks as they developed of Laysan albatrosses. So the amount of plastic in their proventriculus and the gizzard increases as they get older. And then the proventriculus amount of plastic drops starting in late April, but the gizzard amount always continues to increase all the way till late June. So again, these two organs are very tricky and they can really bias what we think we see. So yes, they get rid of the big mass. Well, you know, things like line, things like that often stay, which I haven't gotten into any of that, but there's very interesting dynamics between the types of the material and whether it passes or it gets stuck or all those kinds of things. But yeah, albatrosses cast their boluses. That's the short answer. Yes?
Is there any evidence that shows the plastics that actually kill?
Is there any evidence that the plastics kill the birds? Well, this is the multi-million-dollar question, right? This is what we all want to figure out. So there's three possible ways the birds are harmed by the plastic. The first one that's very obvious, which there's a few published articles on this, is either a plastic bag gets stuck somewhere on the GI tract, or a big sharp piece cuts the GI tract and you get massive infection and so forth. You know, these are really, really, really rare events. I would say we did about, in 2009, we did 72 albatross chick necropsies. We found one chick that had a puncture in the stomach. And it's very clear. You see this ring of white from the acid leaching out, like a little ring of white. 1 out of 72. I've never seen obstruction of a plastic bag or things like that. So that one, the direct mortality, very hard to show. Okay, well, what else could be happening? Well, maybe some people say, if the birds are full of plastic, they don't feel like they need to beg for food, they feel full, or if they get fed by the parents, there's not enough room, or they can't really get the nourishment from the food and so forth. We tried looking for those effects by comparing growth rates. The chicks are growing, then they die. We open them up and we ask, do chicks with more plastic grow more slowly? Do chicks with more plastic have worse body condition? We couldn't see it for both albatrosses and for the Tristram storm petrel. Of course, right? We only look at the ones that die by themselves, which is a big problem, a big caveat, right? If we were doing a cold-hearted experiment, we would randomly assign birds to treatments, right? At the end, we chop everybody's heads off and we would look inside. I mean, that's the way to do this, right? But no, I don't want to do that. Nobody wants to do that. So that path, unless it's very obvious, is going to be not the way to go to show effects. So then there's the third path, which is the indirect effects, more subtle things like the chemicals in the plastic leach out and then they go into their fat. So birds with more plastics in their stomachs have more chemicals in their fat. There's been a few studies like this. The problem is, same with human health, it's so hard to show, this is all correlation, very hard to show cause and effect, There's been some studies looking at development, asymmetry, or the gonads don't develop well, things like that. And that's really that, and those chemical pathways are, I think, the way to go to show effects, but they're very hard, very indirect and confusing. So obviously, I guess my answer would be, right now, if the Chemical Society of America said, we can give you all the money in the world to fix this problem if you show us evidence that albatrosses and storm petrels are being killed by eating plastic, I don't think we'd be able to do that. So I really think we need to know the population level effects, for sure, right? Because there's other things that kill birds that we can do something about. So wouldn't it be nice to know? Maybe we can't solve the plastic thing, but at least we can know how much of an effect it's having. But right now, I think we don't know. Yeah.
So what's the next step in this study? What's the path that this is heading down? You guys can start looking at the fish, or what are the questions you guys can start asking?
Yeah, what are the next steps for our research? Well, this research is very start and go. A new student comes, they want to do something, then we make a big jump. And then students don't want to work on that, and there's a big lull, and then, or we need to write a paper, and then there's a big lull. So even though it may seem smooth, it's a very jagged process. But I think the biggest issue that I'm really getting interested in more and more is I would like to figure out these chemistry paths. And I'm trying to figure out ways that I can use things like stable isotopes to figure out the trophic level of some of these birds and their prey. And then I can figure out those chemicals, some of which only come from plastic, like plasticizers, others which can come from plastics, but also from the prey. And try to put it all together and ask questions like, these birds, given their trophic position and what we would expect of the chemical profiles, do they have an excess of some of the ones associated with the plastics? Again, it's very correlational. It's a way forward, at least to show, well, they're exposed, these are the amounts, and there's very strong correlations with what's in their stomachs. And definitely also another big part is understanding where are they collecting this material. As an oceanographer, I want to know, are they getting it at fronts or eddies, or are there small scale features where this material is really concentrated and available for them, things like that, which for the little species, we still can't really track them yet very well. Yeah.
Similar to the West, I know that there's a big, trying to reduce your single-use plastics here. Do they have similar campaigns where you're coming from those areas, or?
Yeah, so the question is whether there are public awareness campaigns, recycling, avoiding single-use items in this Western North Pacific, where, you know, some of our Hawaiian albatrosses are going over there and collecting material from over there. Unfortunately, I have not heard of very big initiatives. If you guys know, please speak out. I've heard more of the horror stories, I think, you know, about material from one state washing over the beaches of another state, and these huge plumes of debris traced back to certain countries and things like that. So I'm not really sure. Has anybody heard of in the Western Pacific? No, so definitely I think, you know, sharing information and those kinds of things would be very, very useful, because we all have shared responsibilities for the conservation of these species throughout the year, and they, you know, they go into other countries' waters. Yeah. Yeah.
You said that the albatrosses get rid of a lot of plastic in the bowls, and that the young one, the chicks, can do that too. How come when you see these pictures of the chicks that are just full of plastic with dead ones? Do they not have the same ability to get rid of them?
Well, you see, the thing is, it may depend what time of the year the chicks died, right? Usually, we saw the start of the decrease of masses in late April. So the chicks are born in January. So it seems like they cast the bolos towards the end of their development before they leave, starting sort of in, you know, late June. So it could just be a timing issue. You know, maybe some of the boluses are too big or complex and they can be cast, and some birds die at that point, right? It's possible, for sure. Also, birds die for many reasons. When, you know, Terry work, for example, that's studies or published work on why albatross chicks die. The number one reason is dehydration. They're stuck on a little island in the heat, you know. Of course, lack of food because they have too much plastic contributes to that, perhaps. So all these things make it really complicated, you know, but they should be casting their bolos. Yeah, if everything works right.